Picture this. You're walking through a tropical rainforest, thick with heat and the smell of wet earth. Suddenly, the ground beneath you shifts. It's not an earthquake. It's a body, thicker than your waist, sliding past. You follow it with your eyes. And keep following. And keep following. 10 seconds later, you still haven't found the head or the tail. Your brain starts doing the math nobody wants to do in that moment. If the body is already this thick, and this much of it has already gone by, exactly how much more of it is still coming? Welcome to the world of snakes, so enormous that, if they were alive today, they'd top everyone's list of reasons never to go camping again. This isn't a horror movie. It's real history, written in stone for tens of millions of years, buried under coal seams and cave floors on 3 different continents. The good news is, they're all extinct. The not so good news is that science has just figured out why they existed in the first place. And that reason is tied directly to something happening on this planet right now. So before you relax, stick around, because by the end of this video, you might not feel quite as safe on your next tropical vacation. In 2002, a joint expedition from the University of Florida and the Smithsonian Tropical Research Institute set out for La Guajira, in the far north of Colombia, to a place called Cerrejón, one of the largest open-pit coal mines on Earth. The goal wasn't snakes at all. The team, led by paleontologist Jonathan Block and paleobotanist Carlos Jaramillo, was there to study ancient plants and the earliest tropical rainforests, hoping to understand what the world looked like in the chaotic millions of years right after the dinosaurs disappeared. What they found instead would end up on the cover of Nature magazine. Digging through rock exposed by the mining operation, the team began pulling out vertebrae. Big ones. Vertebrae far larger than anything a fish or amphibian could produce. The first instinct of the researchers was to label them as crocodile bones. Because, frankly, nothing else made sense. Crocodilians were common in the fossil record of that time and place, and their vertebrae could occasionally reach an impressive size. Snakes, on the other hand, were not supposed to get anywhere close to this large, so into the crocodile boxes those bones went. The expedition continued for 2 more years, through 2004, and the number of oversized vertebrae kept climbing. Eventually the team had roughly 180 bones on hand, representing at least 28 individual animals, and a mounting sense that something about their crocodile explanation didn't add up. It was a closer look by a snake specialist that finally cracked the mystery. The vertebrae weren't crocodilian at all. They were serpentine, but on a scale that had never been documented before. Every vertebra was roughly twice the width of the equivalent bone in the largest anaconda ever measured. The realization spread through the team like a shockwave. They hadn't found a new crocodile. They had found the largest snake in the history of life on Earth. The animal was formally named Titanoboa cerrejonensis, the giant boa of Cerrejón, and it was unveiled to the world in a 2009 paper in Nature led by Jason Head, with Block, Jaramillo, and their colleagues as co-authors, working from the width and shape of those vertebrae, and comparing them against a dataset built from living snake skeletons. The team calculated that an average adult Titanoboa measured around 13 meters long. The largest individuals in the sample may have reached 14 to 15 meters, which is longer than a school bus, and weighed in excess of 1.1 metric tons. For scale, the green anaconda, the heaviest snake alive today, tops out around 6 to 7 meters and rarely exceeds 250 kilograms. Even in exceptional individuals, Titanoboa is estimated to have outweighed the largest anaconda ever recorded by roughly 4 times, and its vertebrae alone dwarfed the anacondas by a factor of 2 in width. Its girth is estimated to have been as wide as an oil drum, roughly a meter across at its thickest point. If Titanoboa had tried to slide through a standard doorway, the middle of its body would have touched both sides of the frame at the same time, and its head would already be a full body length down the hallway before its tail cleared the threshold. It lived roughly 58 to 60 million years ago, during the Middle to Late Paleocene epoch, only about 5 to 6 million years after the asteroid impact that wiped out every dinosaur lineage except the birds. In other words, the moment the non-avian dinosaurs left the stage, snakes were already quietly building toward becoming one of the most fearsome predators the planet had ever produced. And they did it astonishingly fast in geological terms. No complete Titanoboa skull has ever been recovered, which is itself a reminder of how much of this creature's story is still being pieced together from fragments. What we do have, vertebrae, ribs, and a handful of jaw elements, has been enough to place it confidently within Boidae, the same family that includes modern boas, making Titanoboa a genuine, if almost cartoonishly oversized, relative of the pet store boa constrictor. The find was significant enough that, a few years after the original Nature paper, the Smithsonian built a full-size, anatomically informed model of Titanoboa in the act of devouring a crocodilian, and put it on public display at Grand Central Terminal in New York City as part of a documentary launch. Commuters who had seen plenty of dinosaur skeletons in their lives found themselves stopping mid-stride in front of something stranger, a snake. With no legs at all, long enough and thick enough to swallow a small car whole. It's one thing to read the number, 13 meters, on a page. It's another thing entirely to stand next to a life-size replica and realize your own height barely registers against a single coil of its body. This is where things get genuinely interesting, and where scientists had to pause and think hard about what a snake this size actually implies about the world it lived in. Snakes are cold-blooded, or more precisely, ectothermic. Their bodies don't generate their own internal heat the way ours do. Every bit of energy that powers their muscles, their digestion, and their growth ultimately comes from the temperature of their surroundings. A cold snake is a sluggish snake. A snake in an environment that's too cool for long stretches of the year simply cannot fuel a giant metabolism, no matter how much food is available. Here is the key biological principle that makes Titanoboa so scientifically valuable. The hotter the environment a cold-blooded snake lives in, the larger that snake can potentially grow, because a bigger body requires more thermal energy to keep functioning, and only a sufficiently warm environment can supply that fuel year-round. This relationship between ambient temperature and maximum possible body size in ectotherms is well documented in living reptiles. And it gave Jason Head's team an unusual opportunity. Instead of using known climate data to predict how big an ancient animal could have grown, they flipped the equation around, and used the animal's confirmed size to reconstruct the climate it must have lived in. Using models built from the physiology of modern boas and pythons, the team calculated that for a cold-blooded constrictor to reach the mass and length of Titanoboa, the mean annual temperature in equatorial regions at the time had to fall somewhere between 30 and 34 degrees Celsius. That is dramatically hotter than tropical regions average today, and it stood in direct contradiction to some existing climate models of the period, which had assumed tropical temperatures stayed relatively stable even during past greenhouse periods. In other words, Titanoboa wasn't just a big snake. It became a living, breathing thermometer, one that recorded in its own skeleton the fact that Earth's equator used to run substantially hotter than it does now, sparking real debate among climate scientists about how tropical ecosystems respond during periods of extreme global warmth. It's worth pausing on exactly how researchers translate a pile of disconnected vertebrae into a confident number like 13 meters in the first place. Because the method itself is a small piece of scientific detective work in its own right. Every living snake species has a fairly consistent, measurable relationship between the width and shape of its vertebrae and its overall body length and mass. Measure enough anacondas, pythons, and boas of known size. Plot their vertebral dimensions against their actual measured length, and a clear mathematical curve emerges. Once that curve exists, a single isolated vertebra from an extinct species can be plotted against it, and the model will spit out an estimated body length within a reasonable margin of error, along with an estimated mass based on similar regressions using body width and known density. It's not guesswork, and it's not artistic reconstruction. It's applied statistics, built entirely on the anatomy of snakes that are still alive today. And it's the exact same basic technique that later let researchers estimate the size of Gigantophis, Vasuki, and Palaeophis colossaeus from equally fragmentary material. The trade-off is that the accuracy of any single estimate is only as good as the sample of modern snakes it's calibrated against. Which is precisely why estimates for animals known from only a handful of bones, like Gigantophis originally was, tend to shift so much as better comparative data and more complete fossils come along. The world Titanoboa inhabited was a vast, low-lying coastal plain covered in humid tropical forest, threaded with wide, slow river systems, something like the modern Amazon Delta, but hotter, wetter, and stranger, and Titanoboa was very far from the only oversized resident. Sharing its swamps were at least 3 distinct genera of dinosaurs, an ancient lineage of crocodile-like reptiles that had survived the mass extinction independently of true crocodilians. There was Gigantophis, a large, slender-snouted hunter built for chasing fish through open water, Anthracosuchus, medium-sized but armed with an unusually broad, powerful skull, and Ceratonosuchus, the smallest of the 3, though even it would have made an intimidating meal. The turtles were, if anything, even more absurd. Ceraton has yielded Carbonemys, a freshwater turtle with a shell roughly the size of a smart car. Its skull alone large enough to take a serious bite out of a crocodilian. There's Puentomys, a turtle so unusually round and disc-shaped that researchers have compared its silhouette to a giant tire. A shape that may have helped it soak up more sunlight to warm its cold-blooded body. And there's Ceragonomys, another large podocny-mided turtle from the same formation. Interestingly, some of these turtles may have actually grown too big and too round for Titanoboa to comfortably swallow. Meaning even the undisputed apex predator of its swamp had a few neighbors it had to leave alone. This pattern, enormous crocodilians, enormous turtles, and enormous snake, all coexisting in the same patch of prehistoric Colombia, is exactly what the temperature-size relationship would predict. When an ecosystem runs hot enough for long enough, cold-blooded animals across the food web tend to supersize together, not just the one species that happens to make headlines. It also means that reconstructing a single day in Titanoboa's swamp isn't really about imagining one giant monster in an otherwise ordinary landscape. It's about imagining an entire ecosystem turned up several notches past what feels normal today. Turtles the size of kiddie pools basking on muddy banks. Slender crocodilians patrolling the shallows in packs. Oversized fish moving through water thick with sediment and heat. And, somewhere beneath the surface or coiled in the undergrowth, something with the patience and the mass to end almost any of their days without warning. None of these animals were freaks or evolutionary dead ends in their own time. They were simply what normal looked like in a rainforest running several degrees hotter than anything currently on the map. And for several million years after the extinction that killed the dinosaurs. That was just Tuesday in Colombia. Titanoboa had no venom, and it didn't need any. With a body weighing over a ton, its real weapon was constriction, the same basic hunting strategy used by its much smaller modern relatives. Boas, pythons, and anacondas. It would strike, throw its coils around its prey, and then simply squeeze. Every time the prey exhaled, the coils would tighten a fraction more, closing off the space the lungs needed to refill. Death by constriction isn't really about crushing bones. It's about slowly, systematically shutting down the ability to breathe until the heart itself can no longer pump. Based on the surviving fragments of jaw material, researchers believe Titanoboa's diet leaned heavily toward large fish, suggesting it spent much of its life partly submerged. More crocodile-like in habit than tree-climbing python. Its highly flexible, loosely hinged jaw, a feature it shares with every living constrictor, would have let it disarticulate its mouth wide enough to swallow prey far bigger than its own head, potentially consuming single meals equal to a significant fraction of its own body weight in one sitting. Much like a modern anaconda gorging on a caiman. But fish were very likely not the limit of its ambitions, sharing the water with crocodilians up to 3 or 4 meters long and turtles the size of small cars. A predator weighing over a metric ton had very few natural limits on its menu. Picture it. A slender dinosaur gliding through murky water, behaving as though it were the apex predator of its stretch of river. And then, rising silently from beneath the surface, a mass of muscle heavier than a small car wraps around it in a matter of seconds. There would have been no warning splash, no visible approach, just displaced water, and then a grip that only tightened. That dinosaur's actual place in Titanoboa's ecosystem wasn't predator. It was prey, just like almost everything else unlucky enough to share the water with it. And the only animals in that swamp that could reliably ignore Titanoboa were the ones too heavily armored or simply too enormous to be worth the effort. Like the disc-shaped Puentomes with its improbably round, oversized shell. Here's a part most videos on this topic skip entirely. And it happens to be one of the most fascinating threads in the whole story. Titanoboa was never the only giant snake to exist. It is simply the one we happen to know the most about. Thanks to an unusually rich fossil deposit and a few decades of very lucky mining. Long before Titanoboa was described, the title of largest known snake belonged to Gigantophis garstini, first named in 1901 from vertebral fragments collected in the Fayum Depression of Egypt. Gigantophis lived roughly 38 to 40 million years ago, nearly 20 million years after Titanoboa had already vanished from the fossil record. In the late Eocene of North Africa, early estimates in the early 2000s, based on limited material, suggested it might have exceeded 10 meters in length, and for decades it held the unofficial record as the biggest snake known to science. A more thorough redescription of the material in 2017, incorporating additional specimens and more rigorous vertebral scaling methods, narrowed that estimate down to a still impressive 6 to 7 meters. That's a huge downward revision, and it illustrates something important about this entire field. Estimating the size of a long-extinct animal from a handful of isolated bones is not a settled science. It's a moving target, one that gets refined, sometimes dramatically, every time new specimens or better analytical techniques come along. Gigantophis belonged to an ancient snake family called Madtsoiidae, a lineage with one of the longest and strangest histories of any group of snakes on the planet, spanning more than 100 million years from the very end of the Cretaceous. While dinosaurs still walked the Earth, all the way through to a shockingly recent extinction that we'll get to shortly. Madtsoiids weren't confined to Africa or South America. Fossils attributed to Madtsoia by a close relative unearthed in Argentina back in the 1930s, suggest a snake that reached lengths approaching 12 meters, once again rivaling or approaching Titanoboa territory, this time on an entirely different continent. And then, in one of the more remarkable twists this field has seen in years, the story took an unexpected turn on the other side of the world. In 2024, researchers working a lignite mine in Gujarat, in western India, announced the discovery of 27 fossilized vertebrae belonging to a snake that had never been described before. Dating to roughly 47 million years ago, deep in the Eocene, they named it Vasuki indicus, borrowing the name of the mythical king of serpents from Hindu tradition. A many-headed being traditionally depicted coiled around the neck of the god Shiva. The size estimates for Vasuki turned heads across the paleontology world almost immediately. Depending on which vertebral scaling method is used, Vasuki may have measured somewhere between 11 and 15 meters long, with some of the higher estimates placing it in direct competition with, or even slightly ahead of, Titanoboa for the title of longest snake ever known. The vertebrae suggest an animal that was long and relatively slender compared to Titanoboa's bulk. More built for length than raw mass, though its precise weight remains far less certain than its length. It's worth being upfront about how much uncertainty is still baked into that headline number, because it says a lot about how this kind of science actually works. The research team behind Vasuki, led by paleontologists Sunil Bajpai and Debajit Datta at the Indian Institute of Technology Roorkee, ran two separate regression equations on the same set of vertebrae. One method, based on the width of a feature called the postzygohypophysis, produced a more conservative estimate of roughly 11 to 12 meters. The other, based on a different measurement called the Prehistoric seal width, pushed the number all the way up to somewhere between 14.5 and 15.2 meters. Rather than pick a winner, the researchers published the full range, 11 to 15 meters, and let the uncertainty stand as part of the result. That's not a flaw in the science. It's honesty about the limits of working from 27 vertebrae and no skull. And it's exactly the same kind of caveat that shaped, and later reshaped, the size estimates for Gigantophis decades earlier. What makes the Vasuki discovery so significant isn't just the size, though, it's the timing and location. Vasuki lived more than 10 million years after Titanoboa, on a completely different landmass, in a climate that had already begun its long post-Paleocene cooling trend. Yet a warm, humid pocket of that world apparently still ran hot enough to produce something in Titanoboa's weight class. That tells researchers something important. Giant snakes were not a one-off evolutionary fluke. A single lucky roll of the dice that happened exactly once in the history of life. They appear to be a recurring pattern, one that nature has been willing to repeat again and again, on different continents, at different points in time, wherever the local climate got hot enough and the local ecosystem rich enough in prey to support it. Give the planet enough sustained heat and enough time, in other words, and evolution seems perfectly capable of building another giant snake from scratch. Virtually anywhere on Earth. And it wasn't only happening on land. While Titanoboa ruled the rivers and swamps of Paleocene Colombia, and while Gigantophis and Vasuki were carving out their own record-breaking niches in Africa and India, an entirely separate lineage of giant snakes had taken to the open ocean. Palaeophis colossaeus, described from vertebrae recovered in what is now Mali, patrolled the warm, shallow waters of the trans-Saharan seaway during the Eocene, roughly 56 million years ago. Estimates based on its unusually massive vertebrae place its length somewhere between 8 and 12 meters, putting it in the same size class as Titanoboa despite belonging to a completely different, poorly understood family with no confirmed close relatives among snakes alive today. No skull material has ever been found for the largest paleophytes, so nobody can say for certain exactly what they preferred to eat. But based on comparisons with other marine predators of the period, researchers have floated everything from large fish to small whales as plausible prey. A snake longer than a city bus, cruising a shallow tropical sea that once covered a huge stretch of what is now the Sahara Desert, is exactly the kind of image that makes it impossible to think of giant snake as a purely landlocked phenomenon. Wherever the Eocene and Paleocene tropics ran hot enough, cold-blooded predators seem to have found a way to supersize, whether they were slithering through a swamp or swimming through open water. Which brings us to a chapter of this story that almost never gets told alongside Titanoboa. Even though it might be the single most unsettling one, giant constrictors surviving in the fossil record, right up until the doorstep of recorded human history. In the caves and river deposits of Australia, paleontologists have described two closely related Madtsoiid snakes, Yurlunggur and Wonambi, both named after the rainbow serpent, a major ancestral creator figure in Aboriginal Australian traditions across many different language groups. Yurlunggur, known from Riversley in Queensland and sites in the Northern Territory, lived from roughly the Oligocene into the Miocene, and has been estimated at up to 9 meters long with a body around 30 centimeters thick. More heavily built and more monitor lizard-like in its skull proportions than a typical python. Wonambi nericortensis, its somewhat smaller relative, is known especially well from the Nericourt caves of South Australia, where its remains have turned up repeatedly among the bones of the continent's Ice Age megafauna. Giant kangaroos, marsupial lions, and the like. Wonambi grew to somewhere between 5 and 6 meters. Non-venomous, a pure constrictor, and by every indication it was still alive and actively hunting as recently as 50,000 years ago. Meaning it very likely overlapped in time, and possibly in direct experience, with the first human beings to reach the Australian continent. Fossil evidence and site distribution suggest Wonambi favored a very specific and very effective hunting strategy, lying in ambush near waterholes, where thirsty prey animals like wallabies and small kangaroos had no choice but to come within striking range sooner or later. It's hard not to notice the resonance here. Some researchers studying Aboriginal dreaming stories about giant ancestral serpents guarding waterholes have pointed out how neatly that oral tradition lines up with what the fossil evidence independently tells us about Wonambi's actual physical hunting behavior, long before anyone had excavated a single bone. Exactly why Wonambi and the rest of Australia's Ice Age megafauna vanished within the last 50,000 years is still a genuinely contested question among researchers. And it's worth being honest that this isn't a settled debate. Some scientists point to the arrival of the first human populations on the continent, and the changes that came with them, including new hunting pressure and the deliberate, large-scale use of fire to manage the landscape, as the primary driver behind the disappearance of Australia's giant snakes, giant kangaroos, and marsupial lions alike. Others argue that shifting climate and rainfall patterns toward the end of the Pleistocene deserve at least equal blame. Independent of anything humans were doing, what almost everyone agrees on is the basic outline: for tens of thousands of years, the first Australians and a 5 to 6 meter ambush predator were sharing the exact same waterholes. And then, within a relatively short geological window, the giant snake wasn't there anymore. The Madtsoiidae family, the same broad group that includes Gigantophis, Madtsoia, Yurlunggur, and Wonambi, had already died out across most of the planet by around 55 million years ago. Australia, isolated and drifting on its own tectonic path, turned out to be the one place on Earth where this ancient lineage of giant constrictors kept evolving, kept surviving, for tens of millions of years longer than anywhere else, making it, in a very real sense, evolution's last holdout for an entire dynasty of giant snakes. There's one more Australian contender worth mentioning, if only because the naming dispute around it is almost as entertaining as the animal itself. Fossils of a python, informally called the Bluff Downs giant python, and later formally named Liosis dubudingala, were recovered from Pliocene-aged deposits in Queensland. Some analyses have suggested this python may have reached lengths approaching 9 meters. Which, if accurate, would put a true python, a member of the same family as the pythons in zoos today, in direct size competition with the ancient Madtsoiids that shared its continent. The debate over exactly how big it really was continues, but even the more conservative estimates place it comfortably among the largest snakes Australia has ever produced. So, if the formula for a giant snake really is simply hot climate plus a thriving, prey-rich ecosystem, an obvious question follows: what wiped almost all of them out? The answer, once again, comes down to temperature, only this time running firmly in reverse, after the peak greenhouse warmth of the Paleocene and the very beginning of the Eocene, including a dramatic short-term spike known to climate scientists as the Paleocene-Eocene thermal maximum. Earth entered a long, mostly steady cooling trend that stretched across tens of millions of years, eventually giving rise to the ice ages we associate with more recent history. For a cold-blooded animal the size of Titanoboa, that slow global cooling wasn't a minor inconvenience. It was an existential problem. As average temperatures dropped, these giant constrictors could no longer reliably power the metabolism needed to sustain a body mass measured in tons. The math is brutally simple: the bigger the body, the greater its baseline heat requirement, and as the environment's supply of that fuel thinned out year after year, these giants gradually ran out of viable habitat. They weren't hunted to extinction, and they weren't outcompeted by a smarter rival. They were, in the most literal sense possible, out-heated by their own planet. Smaller, more thermally flexible snake lineages, the direct ancestors of the pythons, boas, and colubrids we recognize today, were far better suited to a cooling world, and they gradually replaced the giants across most of the globe. Only in isolated, persistently warm refuges, like Australia, where Wonambi and Yurlunggur held on for tens of millions of extra years, did any of the old Madtsoia giants manage to hang on into anything resembling recent geological time. Which leaves one more question hanging in the air, and it's exactly the reason researchers keep coming back to Titanoboa's skeleton with new scanning technology and new statistical models decades after its discovery. If global temperatures continue climbing toward levels the planet hasn't experienced since the Paleocene, could evolution attempt that old formula one more time? To be absolutely clear, no serious scientist is suggesting that a modern-day Titanoboa is about to slither out of the Amazon rainforest next year, or even within the next few thousand. Evolutionary change of that magnitude, building a ton-plus predator from scratch, takes millions of years and an extraordinarily specific set of ecological conditions, none of which currently exist anywhere on the planet. And building a body plan like that back up from modern, much smaller ancestors isn't something that happens on any timescale relevant to a single human lifetime. But research on Titanoboa's biology has become one of the more genuinely useful tools scientists have for understanding the relationship between global temperature, ectothermic physiology, and the outer size limits life can reach when environmental heat stops being a constraint. It's a real, physical lesson written 60 million years ago, in bone, And it still holds up today under modern scrutiny in a way surprisingly few Paleocene discoveries do. So the next time you see a python or an anaconda at the zoo, coiled up behind glass, and think to yourself, wow, that's a big snake, remember that. Standing next to Titanoboa, that animal is basically a swimming earthworm with attitude. We tend to assume that dinosaurs represent the absolute ceiling of how large and how terrifying a land animal on this planet could ever get. But the truth, written in the coal seams of Colombia, the cave floors of South Australia, the deserts of Egypt, and the ancient seabed under the Sahara, is that the moment the non-avian dinosaurs left the stage, nature wasn't remotely finished building monsters. It simply traded 4 legs and a tail for a limbless body the length of a school bus. And went right back to quietly, patiently ruling the swamps, the seas, and the waterholes. What ties every single one of these animals together? Titanoboa in Colombia, Gigantophis in Egypt, Madtsoia in Argentina, Vasuki in India, Palaeophis in the ancient Sahara Sea, and Wonambi and Yurlunggur holding out in Australia until almost the modern era. Isn't coincidence. And it isn't some strange evolutionary accident that only happened once. It's a formula the planet has proven, over and over again, across tens of millions of years and multiple continents, that it's fully capable of running. Take a cold-blooded constrictor. Add enough heat and enough rich, prey-filled wetland, and wait. Every time those conditions have lined up in the fossil record, something enormous has answered the call. The only thing standing between us and another one, according to the very research we've walked through today, is the thermostat. It's a strange kind of comfort, honestly, knowing that the only thing keeping a ton-plus constrictor out of the world's swamps right now is a few dozen degrees of average annual temperature, spread out over a timescale of millions of years rather than anything you need to worry about on your next hike. But it's also a reminder of just how directly climate and biology are wired together, in a relationship that has nothing to do with belief or opinion and everything to do with cold, hard vertebral math. Every giant snake this video has covered was, in its own way, a message written in bone about the temperature of the world it was born into. 60 million years later, paleontologists are still reading that message, one coal mine, one lignite pit, and one cave floor at a time. If you enjoyed this one, just remember, as the warning on this channel always goes, you're now officially part of the giant snake family. Hope you enjoy becoming one. Subscribe for more of the strangest, most oversized creatures the fossil record has ever handed to paleontologists. Because if there's one thing this video should have made clear, it's that we've barely scratched the surface of what used to be crawling around down here.